My name is Gabby Berman, and I will be presenting on strong versus weak bases. Strong bases have a pH of between 10 and 14. They are also excellent proton or hydrogen ion acceptors. Based on the Bronsted-Lowry theory of acids and bases, a Bronsted-Lowry base is a proton or hydrogen ion acceptor. They have very high Kb values and therefore low pKb values. Aqueous solutions of strong bases can be observed as slippery or soapy, but if touched, they tend to be caustic and can cause chemical burns. Here is the general equation for a strong base dissociated in water. The strong base, as represented by the BOH, fully dissociates into the cation B+ and a hydroxide ion, OH-, when in water. In this diagram, you can see two solutions, one of sodium hydroxide and one of water. When both solutions are combined, you can see that the sodium hydroxide fully dissociates into a hydroxide ion and the sodium cation. There are equal moles of each ion because the Na+ and OH- are produced in a 1:1 mole ratio. Here is a list of some of the common strong bases. Lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. All of these bases dissociate 100% in water, and as the Arrhenius definition of a base states, when dissolved in an aqueous solution, they increase the concentration of hydroxide, or OH- ions in the solution. When finding the pH of a strong base, you must first find the concentration of hydroxide ions. You then use the equilibrium constant to find the hydrogen ion concentration. You then finally convert the hydrogen ion concentration to a pH. On this slide, you can see the equation for calculating pH if you know the hydrogen ion concentration. Here is an example problem where we will find the pH of a 0.5 molar sodium hydroxide solution. Because sodium hydroxide is a strong base, it is completely ionic and fully dissociates, so each mole of it gives that same number of moles of hydroxide ions in the solution. Therefore, as you can see, the hydroxide ion concentration is 0.5 molarity. You would have to be careful here, because if you had a base like calcium hydroxide or CaOH2, each mole of calcium hydroxide would produce twice as many hydroxide ions in solution. You would now use the equilibrium constant of water, or Kw, to calculate the hydrogen ion concentration. Kw is equal to 1.00 times 10 to the negative 14th. So if you know the hydroxide ion concentration, you can calculate the hydrogen ion concentration as well. After finding that the hydrogen ion concentration is 2.00 times 10 to the negative 14th, you can calculate the pH. By plugging this answer into the pH equation, you find that the pH of this solution is 13.7. Now we will talk about weak bases. They have a pH of around 7.3 to 10. Weak bases only partially dissociate in water. At equilibrium, both the acid and the conjugate base are present in the solution. These are two equations that represent the dissociation of a weak base. Both equations contain a double arrow, indicating that they reach equilibrium. Here's an example of the dissociation of a weak base. When ammonia and water are combined, you can see that the ammonia only partially dissociates. Only one ammonium and hydroxide ion are present because the solution reached equilibrium. Here is a list of some common weak bases: ammonia, methylamine, diethylamine, and sodium bicarbonate. The position of equilibrium varies from base to base. The further to the left it is, the weaker the base. The equilibrium constant measures the position at equilibrium. The lower the value for the constant, the more the equilibrium lies to the left. Here is the equation for the equilibrium constant for a base. We omit water from the equation because if the base is weak, the concentration of the water is virtually constant. Now we will talk about the relationship between Kb and pKb. pKb is the negative log of Kb. And if Kb is increasing, the base is getting stronger. But as Kb gets bigger, pKb gets smaller. The lower the value of pKb, the stronger the base. pKa and pKb equal 14 when added together. You can use the Kb value to calculate pH for a weak base, and you can also solve for Kb using the pH calculations. In summary, strong bases fully dissociate in aqueous solutions, while weak bases only partially dissociate to reach equilibrium. And the farther to the left of equilibrium, the weaker the base. The higher the Kb value, the stronger the base, and the lower the pKb value, the stronger the base as well. Stronger bases tend to have stronger pH values, but pH depends on the concentration of each solution.